So yeah, let's get going. Introduction to Mathematical Neuroscience, Lecture 2. Hopefully everyone's recovered from the I think quite contentful session we had this time last week, albeit with not the best delivery on my part, voice-wise. I'm still a bit husky, as you can tell. And yeah, I filled in some of the content for you guys on the Moodle. So if people were watching, they'll see that there's a slides up there for this lecture now. And there's a post with links to the tutorial notebooks, the one we saw last week, the one we're going to do today. So that content is all up for you guys now, and there'll be more coming as we go. So last time, my clicker doesn't click. Maybe. Yeah, okay. But now have I lost my laser pointer? No, I've got it. Okay, right. Sorry for the blip. So I showed, and this was up on the course website as well, the syllabus. And if you'll recall, and as you can kind of see, I think from the topics, like the idea, broadly speaking, especially for the first more or less half of the course here, is that we're kind of progressing up this exciting arrow of spatial scales that kind of captures, I think, the real essence of computational neuroscience as a field, is that there's things to study at multiple scales. So we had a big overview of general stuff, but then the big meat of last week's lecture was thinking about various ways of modeling single neurons. So we're going to kind of going up, and on the diagram here, that'd be this thing on the bottom left. So we're going to kind of move up this scale. We're up around here now. So the lecture today is going to be about neural networks. Now, neural networks is a big topic. There's a lot of different ways of thinking about this. So what we're doing here is kind of giving us a kind of a smooth movement through what we heard in the previous lecture about ways of modeling and understanding and just things you need to know about single neurons, up to a context of like multiple interacting units. So we've got a little bit of physiology, well, a lot of physiology, but also some more kind of abstract neural network or ML flavored stuff in a bit of a hodgepodge in an intentional way. So last week, just to remind you, because some of this is going to come back, I gave this primer on things that I think are interesting about computational neuroscience in general. And then in terms of single neuron models, we covered quite a few things. We talked about these what we call linear passive properties of membranes, leak currents, and so on. And then active properties, and the active properties are the things that are the kind of interesting nonlinear behavior that's represented in different ways in different models. We went through a few models. We talked about Hodgkin-Huxley in some depth, and Morris-Lacar. Morris-Lacar and Fritz-Nagumo, you can kind of think of, well, definitely think of as a pair, but they're kind of broadly similar as two-dimensional dynamical systems. So that's when we were thinking about the phase planes and thinking a lot about the kind of dynamical systems perspective on the different dynamical regimes of a neuron. And then we talked a little bit about leaky integrating fire models as another kind of level of simplification. And actually, we kind of skipped the Poisson model for reasons of time last time, but it'll come back briefly today. So that was last time. Now we're going to revisit Hodgkin-Huxley today and kind of loop it into some perspectives on simple neural networks. So the plan today, things we want to talk about, is moving on from the things we were thinking about with single neurons. So basically, like we were talking before, like, essentially what makes a neuron fire. That was more or less the gist. What makes a neuron fire, and what kind of dynamics of the patterns of firing and oscillations and so on that we can see in neurons. The next step is, well, a neuron's firing and then it's kind of feeding onto another neuron and it's communicating, right? So that is done mostly via synapses and synaptic responses. So we're going to talk about synaptic responses. We're going to kind of take this into a formalism for a network of spiking neurons, which is I would say kind of alongside networks of morphological Hodgkin-Huxley models, one of the big workhorses of computational neuroscience as a field. Then we're going to segue essentially into some versions of, if you like, the precursors of ML tools that are used regularly, like everywhere in the world today, but particularly the kind of architectural elements of perceptrons and then Hopfield networks, and talk a bit about how those systems encode patterns and kind of function as models of memory. So that's the idea for this lecture. I had this sketch at the beginning of the lecture last week about my kind of John's take on computational neuroscience as a field, essentially. About half the field thinks about information processing, about half the field thinks about neural dynamics of various kinds and physiology. And you know, this little joke about the Holy Grail kind of spanning the two. It's like the Holy Grail is also the hardest thing to do, is to span these two in an interesting way. This lecture, we are kind of doing that. We're going to talk about some things on this side, some things on this side, and kind of cross the boundary, at least cross the threshold, if not like quite tying them together. So, you know, look out for that. Okay, so let's kick off. So as I said, last time we were just thinking about single neurons, about what makes a neuron fire and what are the cellular kind of composition of a neuron that's relevant and stuff like that. So when we start thinking about networks or just groups of neurons, like one of the main representations you see of this kind in neural recordings is something like this. It's called a raster plot, where you have a row for several neurons. You know, these days you can record from like tens of thousands of neurons concurrently. So you obviously can't view tens of thousands of neurons, but you'll have, let's say, a reasonable number, and then t time on the x-axis, and then each of these little dots is neuron fires briefly. So we call this a raster plot, and the events here, these are kind of simplified essentially with respect to the more complicated physiological models or kind of processes we were talking about before last week. This is just an event. It's just a spike. So it's just like spike happened, essentially. So the kind of important fact here is that when we have a bunch of neurons in a patch of tissue, whether it's a very small patch of tissue or a relatively large patch of tissue, they're not in isolation, right? They're kind of connected in sometimes random, like effectively random, sometimes very stereotyped kind of network structures and circuit structures. And we want to understand how they interact and how they communicate with each other. So last time we spent a lot of time thinking about the Hodgkin-Huxley model and some of the lead-in with the passive properties of neurons. Just kind of briefly revisit it. So we had this first differential equation telling us about the evolution of the membrane potential, which is a sum of currents from 4 different places, like an input current I, and then one for each of our 2 primary ion channel species, potassium here, sodium here, and leak current. And we had a kind of auxiliary 3 differential equations telling us about the time-dependent dynamics of these 2 guys, particularly the one here, sodium one, had the evolution of the gating variable of 2 gating variables an activation gate and an inactivation gate for our sodium ion channels. And then over here with our potassium current term, we have this one time dependence activation variable here. Okay, so four-dimensional dynamical system, that was our Hodgkin-Huxley. Now, and what we talked about here most of the time was what's going on with these guys, the K and the Na. And we started with the leak current with the passive properties. And then we talked about I a little bit. So I is kind of sitting here at the front, or if you put it at the end, be plus I, right? And this is input. So what we had last time, we had these step current injections, right? And we're looking at the neuron response to the step current injection, and that was the thing that kind of triggered the action potential. Now, what do we kind of make of that, or what's the role of that term at the network level? Okay, there's two answers to this question. I'll give you the one that I want to focus on first. Actually, the first one is that it's also, if we have some current injection in a kind of network context where we have multiple inputs, then fine, we have a current injection. But we can also think about this I term here as the input from the rest of the network. Okay, so it's kind of representing this here. So if this circle in the middle is the neuron that we're kind of studying, and we're kind of representing it with the Hodgkin-Huxley, or indeed like one of the other models that we were looking at. Okay, so we have something that's kind of telling us about some model telling us how the dynamics behave, how it fires, whether or not it fires. So if we kind of take a step back in the graph or in the network, let's say, so we have, as it's represented here, a bunch of inputs to this neuron from a variety of cells, which could be excitatory or could be inhibitory. And those are all kind of incident on the neuron. These be on the dendrites or on the soma, and those kind of aggregated, and then they, if the input is strong, then that's going to trigger an action potential synaptic response. So the thing that in the single neuron case, when we're kind of studying Hodgkin-Huxley equations in this kind of simplified schema here, that we just think about as an input current, the most, say, kind of ecologically valid, or the most physiologically sensible interpretation of that is the sum of the inputs from other neurons into that cell. Okay, now the way that works physiologically is mostly, I can say mostly and often and most of the time here, for a reason I'll explain in a second, but it's mostly to do with chemical synapses releasing neurotransmitters. So schematically, we've got the neuron that's firing, kind of way over here or way over on like the other side of the street, and then it has its axon, and then the end of the axon is this bit here. So we've had an action potential moving along the axon. Eventually, it arrives here. This is the end of the axon, so we've got a synaptic bouton. And what the arrival of the action potential causes is emission, expulsion of these things, movement of synaptic vesicles to the cleft, to the axonal cleft, and then release of neurotransmitters. And that's kind of neuron A communicating with neuron B. So we get some chemicals essentially kind of pass through the intercellular space between neuron A and neuron B. They're picked up on the receptors on the postsynaptic cell, and then they induce a response in the postsynaptic cell. So have some chemicals mediating the communication between cell A and cell B. So that's chemical synapse. Now these things aren't instantaneous. The synapses are actually kind of quite slow, and they have So the response to the synapse typically follows something along these lines. Okay, so we have like a sharp kick up and then a slow response, but it's not instantaneous. And this response, this activity on the postsynaptic cell is called a postsynaptic potential. And the postsynaptic potential is usually a response to neurotransmitters, or we call it chemical synapse. When I say usually, that's because the other type of the other scenario that I'm not really going to talk about here is electrical synapses, where there's no neurotransmitter, there's no chemical transmission. There is just a kind of electrically mediated communication between cells. And those are interesting for various things, but we're not going to talk about them here. So neurotransmitters, we kind of basically think about two broad classes: neurotransmitters that are excitatory, most of which are glutamate, and then some common like neuromodulatory systems as well. But glutamate is 90% of all excitatory chemical transmission in most nervous systems. So excitatory neurotransmitters and inhibitory neurotransmitters, and then the main suspect there is this compound called gamma aminobutyric acid. So excitatory and inhibitory transmission, and then the little acronym for that we'll use and you'll see a lot is EPSP, excitatory postsynaptic potential, and inhibitory postsynaptic potential. And so the time series for that, if you want to think about it in terms of the postsynaptic response on the membrane potential, is basically similar for the two EPSPs and IPSPs. EPSPs do tend to be stronger than IPSPs, and you get more of them. But well, there's a lot to say about the difference between inhibitory and excitatory synapses that we won't go into here. But the key thing is it's not an instantaneous kind of on-off within like 5-10 milliseconds. It's a slow and a kind of exponentially decaying response. Something that there's also a feature of this that we're not going to talk about today, but it's worth knowing is that the synaptic response is not static. So this is a adaptation response that is quite common in a lot of physiological recording contexts, where basically if you have some input on, maybe it's a consistent train of inputs, then the response at the start of the train might not be the same as the response at the end of the train. So we can have a kind of slowly ramping up or slowly ramping down amplitude of synaptic responses when we have a kind of extended set of inputs. But yeah, we're not going to be thinking about that kind of short-term plasticity here. So the usual or convenient way of thinking about representing postsynaptic responses is with a exponential postsynaptic response equation, where the main thing that matters is the time constant. So we can have a different and our initial condition here. So this would be our kind of a simple equation for a synaptic response kernel, which we can also use as we're going to approximate with this. So we've got our starting value and then our time constant, and that gives us a read off of the synaptic response some period of time after the input. Okay. Now, so that's the initial response. That's the response of one cell to one input. Okay, one spike input. Now we don't usually in a physiologically realistic context, one spike is not really going to do much, and it's not really well, if you're talking about plasticity, then maybe single spikes is relevant, but more commonly we have trains of spikes, kind of come all together, and maybe there's some periodicity in them, but there's like quite a few to deal with, let's say. So the kind of standard way of treating this is to basically think about the spike train as a series of delta functions, and then characterize our postsynaptic response as a convolution of that synaptic response kernel with this series of delta function inputs. So that's the notation for the convolution. And then if we were to write that out with an integral equation here, then we're basically looping over some period of time and then applying our synaptic kernel to our delta spike train series of delta function inputs. Okay. So that's now kind of integrated over time, a bunch of spike inputs. Next up, we need to add in multiple cells or multiple inputs. Okay. So actually one step before that. So what I missed out in the previous is two things: the magnitude and the polarity of the response. Okay, so when talking about polarity, we were talking about whether our postsynaptic response is going to be inhibitory or excitatory. So that was not something included in the previous equation. And then the other part of it is the strength of the synaptic connection from the presynaptic cell to the postsynaptic cell. Okay, so we're going to add in that using this W parameter. Okay, so synaptic weight now. So we're going to scale our input by some weight that it'd be some positive or negative number, and that'll give us a signed input response that we can now think about as this current input term that we were dealing with in our Hodgkin-Huxley. And then if we go, say, the final step and think about many neurons now. Okay, so this was the input of just one cell aggregating a bunch of spike inputs. Okay, now if you remember the schematic, which I think I had, let's go back here. So that will correspond to, say, this cell taking input from this cell, but we have a bunch of spikes. So we kind of had to integrate over time and do that convolution. So if we go to the next step where we say this cell, we're going to do that, but we're going to take that from this cell and this one and this one and this one and all of these. So now we're got one more sum in our equation here. We're going to sum over the number of input cells, sum over J. Okay, so now our input to the cell is the input with a series of convolutions over a series of presynaptic input cells. Okay, each with their own weight, synaptic weight, which could be positive or negative. So this here is a you think about where we started, which was the Hodgkin-Huxley equation. This is now kind of sorry. This is now giving us about, well, this is taking our Hodgkin-Huxley formalism, or the one of the kind of key term in it, from the point of view of the network, this I, up to the network level. Okay. So yeah, going back to the actual Hodgkin-Huxley conductance space model, we had this is a kind of abbreviated version of that equation, where we had 1, 2, 3 for the sodium, potassium, and the leak currents. We're just representing that with a sum over all of our ion species there. Okay, so the active part within the cell, let's say, and then the inputs. Okay, and as I was saying, so then so if we can just swap in I for the thing that we were then looking at there, which is this sum of convolutions with some presynaptic cells. Presynaptic cells is X. That was our synaptic kernel, and we're summing over all the connections. Okay. Plus having our nonlinear synaptic response dynamics in the equation for the memory potential as well. And then the final thing we can add on here is a noise term, because there's usually randomness and uncorrelated background activity in what neurons are receiving that is kind of over and above what they're receiving from the network that we can define. So we usually want to have some noise term in there. And then this here now is, I want to finish up. Yeah. So this is our final formalism for a network of spiking neurons. You okay there, Paza? We disconnected. Okay. Hi, folks. I think you lost us for a bit. Anyone replied on that? No? Okay. Well, let us know if you feel like you've not heard anything for 10 minutes. Otherwise, I'll assume that was just a quick dropout. Okay. All right. So that's giving us this. So the point of what we've been doing here is to kind of take us up from where we left off the end of last lecture, or the things we talked about in the last lecture about single neuron responses, and take that up to a formalism for thinking about networks of spiking neurons. And networks of spiking neurons are, as I mentioned earlier, like one of the main, say, computational workhorses or computational frameworks that are used in computational neuroscience. There are a few, like, say, very commonly used general types of model, and this is one of them. And they kind of scale well, I think is one reasonable way of describing, in the sense of it's kind of an intermediate level of physiological detail where you can have a reasonable amount of some of the ion channel physiology of your cells, but you don't need all of the morphological structure, and then you can have relatively large and complex network topologies as well. So this is basically quite popular. You'll see a lot of this when you're reading about work in this field. Usually, practically speaking, the tools that are used for this are kind of standard and kind of optimized software libraries for running simulations of spiking neurons. And there are two that are the kind of most used ones, which I've got just listing on the screen here for your benefit. One software library called Brian. I don't know why it's called Brian. Is that like a joke about brain? Or I think maybe it's something like Monty Python as well. Yeah, I forget. And another, these are both, I think, from European groups. The second one definitely. So the other one's called Nest. This is from a group in Germany who've kind of driven the development of this. So these are widely used spiking neural network simulators. I would say if you want to get into doing computational neuroscience with spiking neural networks, then looking up these tools and checking out their kind of demos and tutorials and online learning materials is one of the better places to start. We're not going to be doing any of that here. We're kind of going over the fundamentals, and we have some kind of bottom-up implemented examples in the tutorials, which Paz has been driving forward. But they don't, they're kind of toy models effectively. So the thing with these kind of simulations is, like, when you really want to scale up, you need computationally efficient and optimized implementations, and that would be when you would turn to one of these simulated tools, I would say. Okay, and then some of the things you can see, just kind of brief comments, is the kind of dynamics and activity patterns that are interesting in spiking networks are things like traveling waves. There's a concept that's been around for a few decades in computational neuroscience about kind of chains of neurons. They're not necessarily kind of spatially like contiguously laid out in space, but they're kind of paths through networks, let's say. So chains or traveling waves of activation, what they look like on a raster plot. And then another canonical type of thing they're interested in is oscillations. Pretty analogously to what we were thinking about at the single neuron level when we were thinking about, say, this would then be like a trace with spikes, or if we think about the individual rows in the raster plot that we had before, those little blips. So this is the same thing, but this is like a network level oscillation, right? It's a network level oscillation because we have a stripe of dots in this raster plot representation, and then a gap, and then a stripe of dots, and then a gap, right? So this is telling us we've got firing off, firing off, firing off, and the firing is a network level event because all of the neurons or a large number of the neurons are firing at the same time as in a vertical slice. So this is the kind of dynamics that are interesting to study in networks of spiking neurons. Okay, so I'll kind of move over into part 2 of this lecture now. We saw this diagram once or twice. It's going to appear several times. It's a very famous figure, actually, but the point is not necessarily the specifics. The point is to kind of revisit the question of what is the level of detail needed for a given research question. So we were just talking about networks of spiking neurons here. This is actually just for a single neurons, not necessarily thinking about the question of having large numbers of neurons, but well, we were talking about networks of Hodgkin-Huxley neurons, so I guess we'll be over there. But the question that we want to move to now is about when we have a system or the setup that we had before. We have a bunch of cells connected, and we're interested in certain things like patterns within the network. What is the level of detail that we might want to question there? We heard everything. A little bit more of a noise term. Okay. Yeah. Hi, Sharon. So I just seen your comment asking about noise. I'll try and revisit that at some point later on. But yeah, question's been noted. Thanks. Okay. So we're going to move to a more simple representation now. And the kind of history for this is going all the way back to kind of the early days of like cybernetics, computational neuroscience, but I don't think they were calling it computational neuroscience in the 50s. So people were thinking about computation in neural systems, but with kind of a certain schematic type of approach where we think about the individual units as being kind of binary on-off Boolean variables. So this is the same structure. This is more or less exactly the same structure that I was going through. Spent the last few kind of 20 minutes going over in terms of the network of spiking Hodgkin-Huxley cells, but now they're not spiking and they don't have that kind of membrane potential dynamics. They can just be on or off, but we still have these weights, and we still have this summation of some weights going to our input into our postsynaptic cell here. This bit here, which typically in ML and in neural networks is some kind of nonlinearity in the case of the perceptron, it's this rectifying, so it's kind of square wave. I think more commonly, this is going to be like a smooth sigmoid. But this is your activation function, okay? So the thing in the Hodgkin-Huxley model that we thought about a lot is like, what is it that makes it fire? Well, it's the way that these conductances kind of interact with each other as a function of their inputs and so on. So that's kind of that bit. And then the endpoint is the activity of the analog of the postsynaptic cell, okay? Now, this is just, I'm making the same point, describing the same system. I've got some Boolean, in this case, Boolean state variable that's driven by some sum of some inputs with some nonlinear function. Now, one of the things that was introduced by Rosenblatt and the folks who were thinking about this in the 50s and 60s, including Heb earlier than that, is the idea of different learning rules. Okay, so in the case of the perceptron, which is the kind of simple network schema we were talking about here before, there are two learning rules that Rosenblatt was kind of thinking about. One, and these are essentially unsupervised and supervised learning. So the first one is what we typically call Heb's rule, and there's this common phrase: cells that fire together wire together. Okay, and then the general idea being when there are cells that have highly correlated activity, they will have strong weights. Okay, so the rule that can kind of bring us towards that, so this is the notation here is our W prime. The prime is update. So the update is going to be a function of the current weight and then the difference between the kind of neuron A and neuron B. And when that's, if that's a dot product, or when that's small, then we're going to get a or when these two things are kind of similar to each other, then we'll get a small term in there, and we have some learning rate function here. So this is our associative learning, essentially our neurons that fire together, wire together rule. And then the second one that Rosenblatt also introduced, and this is widely used all over machine learning, is in this case it talked about error correction learning, but what is the supervised learning rule? Okay, so we've got some cost function that is defined by the difference between the state, the output state, and the desired output state, and then we're going to kind of scale weights according to some function of this this cost function here. So that's kind of rule 2. Okay. This is just kind of stepping through an example of that. I don't need to go through it together here, I don't think. So the perceptron, the single layer perceptron, and then the multi-layer perceptron, and then the kind of next few, I think, 2 decades of say early types of neural network architectures. This is going from like the 50s, the 60s, the 70s, the 80s. Those were kind of variants on a theme of what we had just now. The difference being something about the topology, so like the number of layers essentially, and the variants on the kind of implementation of the learning rules. And there's a lot more to say about learning rules. One part of that development was led by John Hopfield. This is kind of topical because people probably be aware Hopfield, along with Hinton, and there was someone else as well. Was there a third? Was there a third person? I can't remember right now. Won the Nobel Prize this year, Nobel Prize in Physics, last year. So, and yeah, I mean, I think a lot of people were a bit surprised that Hopfield was included on that, but there was a big contribution to the field of neural networks and the field of computational neuroscience that came from Hopfield, which was his extension of the architecture that we looked at before to think about patterns and attractors and memory. Okay, so the Hopfield network is broadly this equation here. It's think about it as a discrete time linear dynamical system that has what we've got is like activity on our output driven by the states on our input multiplied by weights. So this is this kind of network interaction relationship that we were looking at various points earlier on. And the idea, the kind of insight from Hopfield, is that you can use this structure or use this architecture to kind of define states that can be and they're literally attractors in the system that can be understood as like memories or patterns that the system can kind of retrieve given a certain pattern of inputs on its input layer. Okay, so the way that this goes, I want to move to here. Yeah, okay, so we have two different approaches to doing the time evolution. So this is kind of the update process. The difference between these isn't super important apart from when you actually get down to the implementation. But the main thing is we'll think about kind of graphically. So we have an input layer, we have a weights layer, we have an output layer. The input layer would be like size n, output layer size n, weights n by n. The weights map the input, map pairs of the elements of x and y. Okay. So the idea is that the definition of a attractor or a kind of pattern, stored pattern in this architecture is some set of weights for which when you put a pattern in on the left-hand side, you get the same thing on the right-hand side. So this is the input, this is the output. And the kind of interpretation of that is that this is it's not just the interpretation, like literally what this means mathematically, is that the patterns that are kind of called memorized patterns are stable fixed point in the system. So they're stable fixed points because they don't change. So when the system is in the state of one of these patterns, then as we integrate forward or kind of move the network state along through time, the network state stays on that pattern. So the way that looks as well, I want to show you like the evolution of this. We talked about the learning rules, talked about memorized patterns, talked about stability and attractors. I want to show a quick diagram. Yeah, okay. So we'll come back and cover a few of those points in a second. But I want to give you the visual intuition here. So what we've done in this example is to define. We'll talk through the C code here, but what this is doing is defining and kind of imprinting this pattern. The pattern is going to be an X shape on a two-dimensional grid. Okay, so that's what this thing on the right-hand side is. Okay, so this is our stored pattern, and the difference here from the diagram that we had before. The diagram we had before was like a vector, like a column and then our weights matrix, and then a column for our input and output. Here we've just expanded the states into 2D. I mean, in terms of the way that the weights operate, they're effectively 1D, but we're just kind of representing them in 2D here. And then the pattern that we want to take a look at is this thing. So it's this X on this two-dimensional array. Okay. And so we're going to kind of run the system through, like integrate the differential equations we saw before through time for a given initial set of initial conditions. So these are the initial conditions, and then we're kind of integrating through time. So each of the steps through time, just to be super clear about this, is where was our dx by dt? I want to show. Yeah, okay. So each step through time, we're going to get a new. We're going to multiply x by our weights, giving it. We're going to multiply our states by our weights, give us a new set of states and weights. Sorry, a new set of states, and then we repeat. Okay, so we're going to the states are going to kind of move through a trajectory. And what they're going to do here is going to move towards our stored pattern. So this was our initial configuration, moving through up to 20,000 time steps here. And you can see from this random initialization, we're progressively developing into like retrieval of our stored pattern, because this is the stable attractor that was defined by the structure of the weights. Okay. The way that these systems work is that we have our kind of positive version of our pattern, and the flip, the reversed version of the pattern, so like negative psi. Oops. This is also a stable state. So depending on some aspects of your initialization and other things you can do to kind of play around, you might move to this. Or you might, as we can see in this alternative run here, like we're moving towards the negative sign version of the pattern, but it's the same phenomenon. Okay, progressive moving towards the attractor state of the network. Okay, so one of the useful tools, useful frameworks that Hopfield introduced when he was introducing the general Hopfield network architecture is thinking about the energy landscape of the system. And this gives you a way of quantifying the attractors and quantifying like how many attractors we have in the landscape here. So basically you can just do a relatively simple piece of algebra on the weights to come up with this energy function term or energy functional term here. And then what the kind of heuristic, think about this, is the local minima in our energy function. This is a kind of metaphor, this diagram. It's not a literal representation of the structure because it's a multi-dimensional attractor landscape, but the minima, okay, so see the kind of hills and valleys here, okay? So the attractors, they sit in the minima of the energy landscape. And the way to think about the pattern forming structure of the network is the extent to which we can have an energy landscape that supports the presence of multiple local minima that are kind of separated. So when we have too many local minima, then the separability of the patterns and the kind of stability of the attractors becomes reduced. But this is the way, this is kind of the energy landscape conceptualization of the attractor states in the hot field network. Okay, so I want to wrap up by moving to our returning to our spiking neuron example. So we talked about we kicked off talking about the general framework for network of spiking neurons, building on elements of our Hodgkin-Huxley model. Okay. Hi, Ravindu. I see your question. What are you saying? Okay, good question. I think what I'll do, Ravindu, is I'll finish up because I'm nearly done on the main part of the lecture, and then I'll return to your question and also Sharon's question, and other questions we've got from the room. Okay.
All right, no worries, Professor. Thank you.
Thanks a lot. So first half we were going over this extension of or the formulation of spiking networks, and then we moved to the perceptron and the hot field network version. So it's going to go back in the other direction to where we started. So we looked at this. Okay, this was our where we landed in terms of an equation for the membrane potential of a network of spiking neurons, where we've got some firing rates that are convolved with this response function, and then this local ion channel response, and also with a noise term here. Okay, now, and then in addition we have which I didn't actually go into when I was talking about this earlier. So this X term here, so our firing rate for the neurons in our network is something that we can model with this rate equation. That's a function of the membrane voltage. Okay, but the point here is that this is more or less the same structure as the hot field network that we were looking at before. So we can do the same thing. We can look at the same kind of features that we were looking at in the case of the hot field network. So this is an example of this. It's actually coming from a textbook that I encourage people to take a look at if they want a more granular deep dive on a lot of the things we're talking about here. So this is another kind of raster plot. So we're going over time. The top row here is now index over neurons. And what we can see here is there's these little blocks where we've got, say, a few lines, okay, a few lines here, a few lines here, a few lines here. So this is coming directly from the spiking neural network architecture that we talked about in the first half of the lecture. With the weights matrix that is organized similarly to the hot field network that we talked about in the second half. And what we've got here is the same kind of phenomenon where we've got a few stored patterns in this system, and what these stored patterns look like is certain sets of neurons firing together. Okay, so this is our pattern 1. This is our pattern 2. It's our pattern 1 again, pattern 3, pattern 4, pattern 3 again. Right, so you can see there are some just like shapes in this raster plot that are repeated attractors that are kind of coming and going. And so that's on a kind of spiking raster plot of neurons on the top, and then this kind of corresponding diagram on the bottom is mapping basically like firing rate, a firing rate grouped over a number of cells, and then they're kind of coded with the dot types to just tell us like this is the group of cells corresponding to state 1, group of cells corresponding to state 2, state 3, etc. And then when they're firing at roughly 30, then they're on. And then when they're not on, then they drop down to 0. So essentially, like sometimes we're on, then we're off, then we're on, then we're off. For the case of this one, say the dotted one here, off, on, off, off, on, off, right? The thick lines one here, off, 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 on for a bit, off, on for a bit. Okay, so kind of correspondence between these guys and these guys. So it's got a more involved simulation physiologically than the Hopfield network, but it's the same type of structure. And what we'll have for you in the hands-on tutorial that we'll move to after a break is a simplified version of this, and actually some other things, but a simplified version of this pattern retrieval example in a physiological spiking network model. Okay, so I'm going to wrap up. So we had the first half of the lecture talking about spiking neurons and taking us continuously from what we had in the last one, and then we thought about a simpler type of dynamics, but thinking about kind of pattern storage and retrieval in these Hopfield systems. I think so. Some of the key points here. The network part, so the bit where we move from cells to networks of cells, is always happening via synapses, and it's happening via synaptic responses. Okay, the synaptic responses are multiplied by, they're modulated by synaptic weights. So those two things always kind of come as a pair when we're thinking about neural transmission. And they behave, they kind of correspond to things that we often just study in terms of the I term in all of these models, the Hodgkin-Huxley, the Fitzhugh-Nagumo, the Morris-Lacar. Like whenever we were doing those kind of phase plane analyses or other things that you often study in the simplified case of a single neuron model, usually like the way to think about the I term is like the inputs from the other cells in the network, or at least that's one way of thinking about it. Okay, and then we talked a little bit fairly briefly, moving quickly on perceptrons and Hopfield networks. You know, it's a conceptual model of memory storage and retrieval, but they're also attractor networks that are kind of certain type of canonical dynamical system. But we can also study the same kind of behavior that we see, say, more clearly and more simply in pattern retrieval in Hopfield networks with networks of spiking neurons as well. Okay. Questions? And we already had some questions on the chat, and we'll have some in the room as well. So you guys in the room have a think, and I'll have a read what we've got over here. Okay. And then there was a question about the noise term. Okay, so 3 questions on the chat here. I'll go through each of these. Oh, someone's joining from Copenhagen. Fantastic. Okay, so there was, I think the first question was about noise.
Yes, I think it was about the Hodgkin-Huxley equations, the external inputs, the ionic currents, and the noise term. I think it was.
Yeah, but I don't see it on here, but I saw it on there.
Oh, because they reconnected again.
Okay, right. So the question, to repeat for the recording and so on, was Shirin said, would love to know a bit more about that noise term. That sounds like someone who would work with Jeremie would ask that kind of thing. Okay, so I'll go back and we'll talk about it. I'm afraid I don't have a lot to say about the noise term per se here, but we'll go and talk about it. Was here, yeah, okay. So this was kind of the end point of the progression in the first half, right? Where we kind of have our network contribution to the rate of change of the membrane potential. We have our time-dependent ion channel flux contribution, and we have our noise term here, which is the question you're asking about. Now, what to make of it? Well, so usually the way that we will deal with noise term like this from a modeling point of view is it will be some random variable that is just an additive noise term, and it will scale by, you know, square root 2D if you want it to behave well from a numerical integration point of view. So this noise term will be like random Gaussian noise being added from a numerical point of view, like added at each integration step, and just making things blurry. Okay, that's say mathematically speaking, numerically speaking, what the noise term is doing here. Physiologically speaking, one or two things to say about this. So the idea, the rationale for including noise in neural models in general is that there's some structure. It's kind of the same as noise in, I guess, like a regression model or something like that. There's some structure that we're describing, and there's some structure that is not included in our description. Okay, and by structure we mean some, you know, fluctuating additive input to what everything on the right hand side here, which is going to determine the ups and downs of the memory potential, and then potentially whether or not it crosses its threshold and does interesting stuff. So what does that mean, like having some random input term in your description of a neuron? Well, if we go over to the bit that is defined here in terms of the inputs, which is this first term, okay? So here we're effectively saying we know everything about a network that is defined over like index J here, right? So we have a network of n neurons. We know all of their connections. We know what their activity is according to these equations, and they communicate with each other and give us some inputs according to the system that we've set up here, right? So the noise term is basically the physiological interpretation of this would be, well, there's also some other stuff. There's maybe some other neurons that are not in our network that we've explicitly modeled. They're, say, also present in the tissue. Maybe they're far away. They're, you know, however you want to think about, like, not included in the network model that's explicitly defined here. But there's still some neurons that are giving us some incident input. But then what's different is that we don't then have much to say about what the kind of structure of that is, because it's undescribed. So we'll just make it random. We'll just give it some kind of random statistical properties. Now there's other things that could correspond to as well. For example, depending on what you're looking at, but certainly in the case of individual neurons, there's kind of thermal contributions to the membrane potential fluctuations, especially when you get down to like very small cells. So, for example, there's interesting work on spontaneous generation of action potentials on axons of small axons. And the idea, if I remember this correctly, is Aldo cell, is that so you can basically, there's some, if you look at a small axon in certain physiological preparations and you can kind of model this clearly as well, but you see like spontaneous generation of action potentials. So some axons will just, and this is an axon, this isn't a dendrite, it's like an axon will spontaneously fire. Okay, now the thing that's different between an axon and some dendrites or a cell body is axons don't have lots of inputs into them. The axon, I mean, there are some cases of like axonal synapses, but essentially like an axon is getting its input from the cell body, which determines that the cell fires, and then it just propagates its firing along the axon, right? The axon is not receiving inputs from lots of other cells. The inputs from the other cells are going into the dendrite, going into the cell body. They determine the firing, and then and then that moves along the axon. So there's no kind of complex network structured input. So that's important because the generation of these spontaneous action potentials in axons is a thermal phenomenon. So there's basically like just literally like noise in there's I feel like kind of electrochemical randomness in the opening and closing behavior of the ion channels that has a certain amount of just thermal fluctuation, like local thermal fluctuation. So the reason why I'm kind of going on about this is like that's an example of something that would be a noise term in a model, like a Hodgkin-Huxley model, where that is not something that you would interpret as or describe as or think about as random background correlated activity. It's a different type of noise, right? It's like physical noise. So there you go. Kind of two ways to think about noise terms in neuron models is like thermal, physical, or electrochemical noise, randomness in just the behavior of your components, like your ion channels, or it could be activity of things like cells that are present in the tissue, but that aren't kind of described within the model, the rest of the model that you define in your equations. Okay, so that's like physiological definition of noise. And then maybe the final thing to say about that is what does it do for the dynamics? And then there's what to say about that. But broadly speaking, the thing that noise does the most, or I think the most kind of relevant role of noise terms in terms of how these systems behave in ways that we care about, is somewhat similar to the input current term, is they kind of give like a kind of background boost to the kind of ambient membrane potential. So if we don't have the I term here because we replaced it with the network term here, but we should also have an I term here, like plus I, where that I means literally like an actual current injection, which you may not have at any given time, but you could potentially have some current being injected into tissue that isn't something that's coming from other neurons. It's coming from like an electrode in the experimenter preparation that is literally injecting current, right? Or indeed something like a transcranial magnetic stimulation input, which is the kind of things we work on. So you'd have another I term here in general that could be mostly silent or doing stuff depending on your experiment, but that as well would be giving you say when it's on, like we were looking at last time, say like a kind of square wave input of a current injection that's like just boosting the level of the membrane potential, or like depolarizing the level of the membrane potential in a just kind of static, non-dynamic form. It's just like a straight current injection. So the noise term kind of behaves a bit like that, but the difference is that it's not just like a square wave current injection. It's going to be kind of moving up and down, right? But the extent to which it moves up and down, like the amplitude, would be something that is to do with the amplitude of the noise term. But the impact of that is going to be similar to the impact of a square wave current injection, in the sense of like at certain points it's going to move the the entire system, like the entire right hand side of this equation, close to some firing threshold, and then stuff happens, right? So so both the noise term and a current injection, and I guess to be complete, like whatever the inputs are here, these are all parts of this equation that can kind of move the neuron or move the neural population into, say, cross some threshold point, and then move into one qualitative regime or another qualitative regime. So that's, I think, the most useful way to think about noise. Other things you could say about noise, but I talked for a while there, so I'll stop for now. Great, thank you. Yeah, sorry, yes, question.
Random coefficients plus two.
Sorry, you're saying there's a reason why we can, or we shouldn't be able? Well, okay.
For the
Why is there no noise in these terms? Right. Okay.
I think there's like two different ways you can associate what the noise term means. One is just saying like, error measurements, which is like basically you're right. There would be justification to kind of like say there's fluctuations in this term as well as the other term. So let's just add another noise term. But then, as John was saying, we can add the noise term not as just a representation of randomness, but as a representation of other dynamics that we just don't know about yet. Like we know that they exist, we just don't know what they are, but they want to be like, give it credit, give it the kind of like placeholder representation that there is some sort of fluctuation going on here. I just don't know what it is. So I'm going to substitute that for a sort of a noise activity.
Yeah.
So in that case, it wouldn't be necessarily randomness or error in your terms. It would be just a placeholder for another unknown dynamics.
Yeah, I would agree with that statement. And and I guess to continue with it, I mean the scenario I was saying where we have the thermal noise scenario, right? So like in principle that could be written out as some noise in some of the terms here, like even in the gating variable equations, right? So if we know what the noise is with respect to the other parts of the system, then we could define them as noise components, like stochastic components in those terms. But in this context, it's really just kind of, the part of the ontology where we don't have much to say about it other than some randomness, as Paza was saying. But yeah, it's a good question. Another related or kind of adjacent thing that comes up is whether your noise should be additive or multiplicative. And that has a big effect on how things behave numerically. So then you get into some questions about what do you think your noise is, right? So if you have, so the difference here, guys, would be like additive noise is the simple case where you don't actually need, what you can do and what you should do when you're, say, doing this numerically is you kind of define some big long array of like rand n numbers. So just get a bunch of Gaussian samples, and then you can lay out your noise array, like the thing that you're drawing from this term, and it actually is it's independent of the state of the system, so that you can just kind of like grab numbers from your noise array on every integration step, and you don't have to change your noise array as you go, because it's independent, and it's additive. Okay, that's the idea of additive noise. Multiplicative noise has basically the noise at this point doesn't add to the noise at the previous point. It multiplies the noise at the previous point, which means that the kind of state, it's like a time varying state, the noise variable, and it can do things like explode, like have very like larger amplitude effects than an additive noise. And it's kind of, you have to be more delicate and attentive to how you deal with that numerically. But we don't usually worry about this needing to be a multiplicative noise term. We just think about it as additive. Okay, good question so far. And so next question was Ravindu. Says, hi professor, when you say the pattern is a stable fixed point, does that imply each of the points on the diagram are fixed points, or the entire structure is a configuration that is stable? Practically speaking, what do these patterns mean? So I think a clear answer to that, Ravindu, is the second. No, the first one. Each of the points on the diagram are fixed points. That's what we're talking about. So yes, we have a bunch of fixed points. We have a fixed point for each pattern, and the behavior of the system, as we kind of saw here, so is we kind of move towards the fixed point, right? And then the definition of the fixed point is like when we get to this point, eventually, then actually I guess we arrived there at T4000, right? So we arrived here, and then we kind of stay in this for the rest of time. Okay, so yeah, it's literally a fixed point, and there are multiple fixed points depending on the structure of the weights. Okay, and then the second part of your question is, practically speaking, what do these patterns mean? So the idea, I think there's a recent or a kind of famous quote from Hopfield. So like the idea that was to some extent introduced by the Hopfield network in the 80s, I guess to some extent by the prior work as well, is it's a kind of conceptual model of how memory works, right? Memory in neural networks and memory in brains. And so to your question, like practically speaking, what do these patterns mean? I'm not sure what the best answer to that is, but the idea in terms of what they mean from the kind of concept that they kind of developed in the computational neuroscience context is this is how memory works in neural systems, or sorry, this is how memory can work in neural systems. And then I think Hopfield and others be kind of agnostic as to how good that is as a real fully accurate, say, description of, memory of the kind that we think about in natural language, in humans going about their daily business. But it certainly is like one general theory for trying to understand like what memory is in terms of a network structure. So there you go. Maybe that's one way of thinking about what they mean. Mathematically, they're fixed points. Okay. So then third question is from Shirin. Could we think of the energy field in the Hopfield network analogous to a closed system in physics where local entropy decreases as the network evolves towards stable fixed points? Local entropy decreases as it evolves towards stable fixed points. I think so, but I'm not sure if I can go much further in my answer to that question, essentially. So I'm gonna say yes, and leave it there. But yeah, happy to kind of talk more about that, Shirin. Okay, questions from the room. Great. What's your name, by the way? Jonathan. Next. Mhm. Oh,
But yeah, so said like, I think it was even like one of the first times it showed up. Or that might have been. Said that maybe something along the lines of the goal was that the X and the Y will match after the weights. So if I'm understanding that like the matrix multiplication correctly, does that mean that the output is either like an eigenvector, like a scaled version of the input, or is the same thing as in that matrix as the identity matrix?
Okay. Let's say that. So say that again.
So like, you do X matrix multiply W spits out Y, right?
Mhm.
Is it- Or am I misunderstanding the?
It's not exactly that. So it's
Okay.
not saying like the input should be exactly as the output. There's
Okay.
actually a stable pattern and the tractor state that we want the system to converge to.
Okay.
And so this is different from the input. So what we want to do, our objective here is the network to reproduce at the end the same tractor state that we want to reproduce. Now we can initialize it in many different states. And we can observe that this initial state will change based on this matrix multiplication, and whether or not, and it will obviously lead to a final state.
Yeah.
And we don't want the initial state and the final state to match. We want the final state and the stored pattern state to match. If that makes sense.
Okay, so it's almost like you have input some initial state that's not hyper specific.
Yeah.
You adjust the weights eventually until the output matches an answer that you already separately had and you have it.
Yeah.
Supervised learning kind of.
There's different ways to go about it, but that's one way to go about it, saying that I'm gonna adjust the weights in my matrix such that the state that it evolves into is a state that I previously intended to, but not explicitly gave it.
And in this case, you already know those, you already know what those previously objectives cut states that you're looking for.
That is what you actually use to determine what the matrix, the weight matrix is going to be. This is
Yeah.
actually covered in the tutorial as well. So,
Yeah.
you know,
Okay.
Yeah. So there's there's kind of I think the thing about Hopfield networks that is different from more kind of conventional recurrent neural networks is that you define the patterns. You like design them literally, like you kind of say this is the pattern, you know, write down some numbers, write some code, imprint the pattern on the network. It's not like learning process to find some configuration that then is like the weights that you know, minimize the error function, right? It's you kind of state essentially you hand wire them in more or less, and then kind of study the retrieval process.
And so how did that continue to the X? Were those two, not sure if those are two separate.
The same thing, yeah. So this is kind of a 2D, you know, state
And does
representation.
this, kind of represent the continuous adjusting of the matrix until it, or
Not the
the matrix
matrix,
doesn't
the
exist.
states. The matrix is fixed. So the matrix defines the attractors, and then the states is the X, okay, and the X evolves over time.
Okay,
But
so-
the way the X evolves over time is repeated multiplications through the weights matrix. So you're just kind of propagating the states just like rippling the states through the matrix until eventually they end up in where they end up, and that's the stable point.
Okay, yeah, that's kind of analogous to like, or I guess, like learning algorithms and stuff like that, or like more traditional machine learning.
It's a strictly feed forward mechanism.
Yeah.
There's no
Yeah.
Okay, interesting.
It's recurrent, but there's no feedback. Yeah.
It's the network is recurrently connected, but there is no updating, recurrent updating. It's strictly like the updates are
Yeah.
happening in the forward passes.
Yeah. The weights are not updated.
Right. Yeah.
Yeah. Great questions, guys. Any other questions from the room? No? Okay. Any other questions from the chat? No? Good. Okay. So we'll take a quick break. And then we'll come back for our tutorial. So I see it's 3:32, so we'll reconvene 3:40 and have your browser opened and signed into Google to use the Colab notebook that will give you the link for is on the Moodle, and we'll also put it in the chat as well. Okay, so see you back here in 10 minutes. So this time, Parser is going to lead the tutorial for two reasons. One, because he made it, and two, because it means I can put my feet up. Not really, but I will be perched over here in the corner, kind of making some notes and asking some questions. Hopefully the folks on the call can hear that, even though I'm not facing the microphone. Yeah, I handed over the power mic to Parser, so he's officially in charge. But why? Yeah, I'm gonna do my best to kind of make some additional comments and maybe interject or ask questions about things in the tutorial that are going to be related to some of the things we've been trying to get across in the lecture. So, by the way, the people who were kiddos and grabbed the slides that I posted this morning, there were a few changes to them since the ones that I posted. So if you want to keep your files up to date, then just go grab them in a few hours and kind of upload the most recent version. There's not like a significant change, but if you want to have exactly the slides that we used in the lecture, then just re-download in a few hours.
Is anyone ready to go? Everyone downloaded the notebook working correctly? Okay, then let's get started. So the layout of the tutorial is pretty much the same as the lecture. We're just gonna go through the same progression as the lecture, but now we have a kind of hands-on code that'll actually implement the stuff that we talked about already. The flow of it is going to be starting very local, very small at the level of synaptic communication, synaptic transition. That's part one. Then we're going to move towards extending that a bit towards just having, instead of just having the synapse, having a presynaptic neuron and a postsynaptic neuron. And then adding another level of complexity to that in part three, which is adding multiple presynaptic neurons. And then in part four, we're gonna turn that modular multi-neuron into like one postsynaptic neuron into a fully integrated network. So all neurons will be connected to each other. And when that happens, we can actually see some interesting dynamics emerge, which we'll go over. And finally, we're going to make it more biologically plausible with the insights that we learn along the way to have a network of neurons, which also follow biological patterns. Okay, so let's get started. So neural and synaptic dynamics. So this is essentially the same thing that John was telling you about. Here, we're trying to approximate the, let me just run it real quick. We're trying to approximate the transmission of signals from a presynaptic neuron to a postsynaptic neuron at the level of the synapse. So if you remember the figure in the slides, it was a bit of a delayed rising and then decayed falling. So a mathematical function that would approximate that same behavior would be a exponential decay function. And this exponential decay function is parameterized by two parameters, eta naught and also the time constant. And so here, if you run this the cell, you can see how these different parameters would influence the shape of our kernel. So this would be the kernel that we're going to be using to convolve the spike trains with to get a postsynaptic membrane. Whoa, what just happened? So yeah, so here it's pretty intuitive. As you can see, as we increase eta naught, the overall amplitude of the kernel just increases or decreases. And if we adjust the membrane time constant, we can see how fast or how slowly this decays. And now, so this is just at the level of a single synapse. But now if you want to extend this to say, oh, how does this actually interact with a spike train? This is what we get. This is part 2. And at any point, if there's any questions, just let me know, because in that case, it's going to be a pretty quick tutorial. So here, what we're saying essentially is that we are going to have a, here, we're going to have a presynaptic spike train, and this presynaptic neuron is going to use this kernel that we just defined to induce a postsynaptic potential in the postsynaptic neuron. And the way that, and the presynaptic neuron's firing rate is generated via a Poisson process. So here, the first two parameters are essentially the parameters defining our kernel, same as before. And the bottom two parameters are more related to the presynaptic neuron, saying how fast it's firing, the firing rates. And then we also have a parameter for the total time of the simulation, which is not that important, honestly. So just playing around with it, let's see what happens if we increase the eta naught parameter. So what do you guys think is happening here? It's not too complicated, but just to build some interaction. What happens if as we increase eta naught in the postsynaptic potential? Yeah, exactly. So the postsynaptic potential just increases. You get a stronger response because your kernel is just giving you a stronger convolution in the beginning. Now, if we decrease the membrane time constant, what that maps onto is a faster decay in this in the postsynaptic potential. So when this happens, it's harder for signals to integrate. But if we increase the time constant, we can see here that we get generally a higher sort of postsynaptic average. So this is because by the time that the signal from the first impulse is going to decay back to 0, the second pulse is going to come in, and it's just they're gonna add up and add on top of each other, and they're going to integrate. So we're going to get moved closer to the membrane threshold and firing. So now what we have here so far is the synapse, and if extended to a neuron, presynaptic neuron, and postsynaptic neuron, then what we're going to do is actually have multiple neurons connected to each other, at least multiple presynaptic neurons. So the diagram of the structure that we have here, this is the perceptron model that we were going through in the course. So here we have a bunch of presynaptic neurons, 10 presynaptic neurons, and they're connected to a postsynaptic neurons, each of them with their own weights and their own activity patterns in the terms of firing rates. And the signal from each of them are going to be, spike train from each of them is going to be convolved by the kernel. And in the middle here, at the end here, this signal from all of the different neurons are going to be integrated into each other, and that will give us a summed up value for the postsynaptic membrane. So as we can see here, it's hard to, maybe I should make it a bit larger. Well, that's much. Okay. So here we're seeing the activity patterns. The way that this is working is that we have, for the presynaptic neurons, their activity is determined by spike trains. So it's not membrane voltage, but this is just action potentials and spike trains. And the spike trains are going to get turned into voltage. And then this voltage is we're going to define a threshold for this voltage, saying that whenever it passes a certain threshold, the voltage at the postsynaptic neuron is going to generate an action potential. So essentially, we're starting off with a spike train for each of the neurons, and we're ending with a spike train for the postsynaptic neuron as well. So this is how it goes. Spike train, convolution, integration into membrane voltage, thresholding of the membrane voltage, back to spike train. So any questions so far? The blue and red over here? Oh, yeah. So the blue represents excitatory connections and the red represents inhibitory connections. And you can play around with this to adjust the ratio of the EI to see how that would influence your integrated membrane voltage. So if I increase the inhibitories a lot, then you can say, like, they barely pass the threshold, which is pretty intuitive. And you guys can just play around with these variables. It's a nice toy model to kind of, like, vary different parameters to get that intuition of, like, how these things work. Yeah, exactly. So convolution of the spike trains here with the same kernel. And yeah. So, okay. So again, we have the spike, we have the synaptic transmission defined approximation. We can approximate it mathematically. Then we extend it to a spike train into a membrane voltage. Then we add a bunch of different neurons together, seeing how they would actually integrate with each other and how they would sum up. Now, what we're missing here is to actually have a network that's fully interconnected. So that's how we want to approximate a neural network, right? Or a neuronal network. So it's not as straightforward of just, having a presynaptic neuron and a postsynaptic neuron. It's much more scrambled together. Every neuron is connected to each other. So we want to have a model where all the neurons are fully interconnected. So for that, we're going to be using a Hopfield network, which is, again, a mathematical simplification of how this would happen. We're gonna leave aside a lot of the biological nuances that we have described so far and go back to the basics for this part. But then we're going to introduce back these biological interactions at the end. So let's talk about Hopfield networks. So with the Hopfield, the structure that we're doing is that we're trying to make a biologically plausible yet simple. Oh, I thought you said you can say that again. There we go. Is that good? Okay. So Hopfield networks. So we went through it pretty intensively during the lecture slides, but here I will try to give you a more intuitive explanation, just to be more comfortable, like, thinking about it. You can refer to the notes and the lecture slides as well for more mathematical rigor, but I'll try to give you a more of a kind of like explanatory definition, more intuitive definition of what it means. So there's two things that are pretty important in Hopfield networks. First of all, it's a simplified model where the neurons get to only be in two states, up state or down state, -1 or +1. So there's not much of activity, and so it's not a continuous voltage, or it's not a yeah, it's not a continuous voltage or like a specific firing rate that the neuron has. The state of the neuron can be in just two states, but the connections between them, they can be any real number. So, you know, -10, -2 doesn't matter. It can vary a wide range. So the structure is pretty simple. You know, it's just that the states can be only in two states, and they're all interconnected, and the weights are real numbers. Now, the other important bit to this is the update rule. So the update rule is essentially just having the structure plus the update rule will interact in ways that we will see some pretty interesting emergent behavior, such as memory. Memory will start to emerge if we just have these two principles. So let's talk about the update rule. What does that mean? It's pretty simple. It's just telling you how the states of each neuron should change based on the input, the incoming connections to it. So imagine we have 10 neurons, and they're all connected to each other. And if we look at one neuron, we want the update rule is essentially telling us if the state of this neuron is congruent with the incoming connections and the state of the presynaptic neurons. If so, leave it be. If not, flip the sign. So what does that mean? If, for example, imagine your neuron is in a positive state, right? And the neurons that are connected to it have a negative connection weight, but they're all themselves are in a positive state. So if they're positive, but their connection is negative, that would imply that this neuron should be in a negative state, right? But we see that it's in a positive state. So the update rule here says flip it. But if it's, for example, if it's in a negative state, and the neurons are in a negative state, and the connections are positive, everything's good. Everything makes sense. So then in that case, the update rule says just leave it be. So it's a pretty simple update rule. It's just saying flip it or leave it be, and that's all that's happening. And from these simple, any questions about that so far? Because that's essentially like, you know, the bulk of top field networks, that those two elements. Yeah.
So I think that's allowing like switching sides. Is that found in the matrix?
Yeah. So it's essentially multiplication of the states of each neurons multiplied by the matrix, and you take the sign of it. You integrate. Okay, so here you have the weight matrix, the states of the presynaptic neurons, and you integrate it. You integrate all of them, and you take the sign of this integration. So remember how we said that the neurons can only be in an up state or a down state? So essentially, you only care about the sign of it, right? But the weights can be like -10, or it could be, doesn't have to be only binary. So imagine here, the incoming signal is going to be like -10 multiplied by -1. It's going to be -10. We take the sign of it, it's going to be -1. And that's going to be the state of the postsynaptic neuron. But yeah, it's all just multiplication of the connectivity matrix by the state of the presynaptic neurons. And interestingly, I forgot to mention this, there's two ways we can actually go about this updating. There's an asynchronous updating method, and there's a synchronous updating method. The synchronous updating method is saying, like, you have a clock cycle, where you look at every neuron and update this the state of them based on the interaction that I just explained, all together, all at the same time. But there's another more biologically plausible way of doing it, which is an asynchronous updating. Essentially here, you're not updating all the neurons at the same time. Rather, you're just picking one at random and checking the connections and the state of the presynaptic neurons to it and seeing if that's congruent or not. And then flipping that and then moving to another random neuron and then moving into another random neuron. So it's a much more random process. And so here, we're in this example, in this neurons, we're following the asynchronous method. So here, I'm going to be going through 3 different concepts here for the half field network. The first one is this energy. And no comment, no questions in the. Okay, so I'm going to go over then this energy landscape definition. What does that mean? So this energy landscape is essentially talking about the stability of the network. So the lower the energy, the less, or rather, let me explain it this way. A low energy state corresponds to a state where no change is happening, which is kind of like intuitive. Like imagine physical systems where it falls into a stable state, the energy is pretty much low. So here, this is what energy is defined as. It's not necessarily defined as the same energy in joules that we see in physical systems. It's just defined as this, the state where if there's a probability of change happening or not. The lower energy states means that it's a state where changes are not happening, or it's a quote unquote, or it's essentially a stable state. So that's how it's defined. So this is, imagine we have a connectivity matrix, and this is a connectivity matrix of 10 neurons. Imagine we initialize our 10 neurons in a random state over here, right? We want to see how this energy of these states evolve over time based on this update rule. And we can send these asynchronous update rule. And we it left time pass through different iterations, we can see that it gradually falls to a a lower energy state. It falls into a local minimum. So, and it does so gradually. It doesn't like instantly happen. So we just have to let it run, let random samplings of different neurons, and those flippings to run over multiple iterations, so that it eventually falls into a stable state. Yep.
Does that mean that correlate some ability to learn or generate some sort of stable memory with kind of like in like an intuitive way where it's like, I no longer have to put energy to this, it's kind of this naturally like this is the answer. Like you're not combating your idea anymore. Like think of energy like a way like, I don't know, like neural friction almost causing you to like debate whether or not this is the correct answer or not. It's like a correct answer, and it's no longer big like energy consuming idea. Like you run it that way.
Right. So there's
like the lower the energy implies a stable
so
learned mechanism or like a memory.
so there's two things that's it's important, but you're in the question that you're asking. One is a learning mechanism, and one is the energy of that configuration. The learning is happening as the change in the weights of the connectivity matrix. The energy state, however, is related to that, but is more specifically defined in the states themselves. The probability of the states to be the tendency to want to flip or not. So you could have a high energy state without needing to really change the connectivity matrix that much. You can, for example, have a connectivity matrix that's already pre-learned, but you initialize your system in a very far away state as its learned state. So in that case, it would have a higher energy state. But if you initialize it very close to its learned state, then it would have a lower energy state. So they're kind of like, they're a bit different, but that is not to say that the configuration of the matrix itself has nothing to do with energy, if that makes sense.
But at the very end, when it converges to a stable state, is there a correlation for low energy as well?
Yes. So when it converges, this most stable state is a state where it's the lowest energy. Okay. So here, let's see what's happening here. It's essentially just showing you that. This plot right here at the bottom maps onto the middle plot. It's just plotting every fifth iteration. So like 0, 5, 10, etc., etc. So we can see here that if we initialize the system over here in this configuration of neurons, then after 10 iterations, it falls into like a semi-stable state. But then after a couple of more updating, it falls into iteration 20, it falls into a state where it doesn't change anymore. So this non-changing maps onto a low energy state, as we're seeing it here. Now, there are different parameters that go into it. This defining of this energy, for example, like to see what happens when we increase the number of neurons. So we can get like much lower energy states as well. But then it might take more it might take longer. Instead of 20 iterations, might take 25 iterations to fall into that state, energy state. We can, let's see, we can initialize the system much farther away from its attractor state. And if that happens, well, this is kind of random, but ideally it should take, again, longer to fall into that lower energy state. But not always, because this is random, but essentially that's the idea.
And so say that a system that can fall into a low energy state faster would be ideal. We're trying to seek out.
Good question. So it depends on what you want to do. So this will kind of like this falling into a stable state is akin to saying that there's a memory, quote unquote, embedded into this network. Wherever I initialize it, it falls into this kind of configuration of neurons that has the same pattern. It says it has it within it has captured this memory of the state that it can reproduce, even if I just initialize it somewhere far, right? Now, if I want to have a high accuracy of retrieval, and we're going to cover this as well. If I want to have a high accuracy of retrieval, which is, it would be what you're saying, like, fast convergence to that memory state, attractor state, as soon as possible. However, sometimes what we want to do is actually use the same number of limited neurons that we have to actually encode as many memories as possible. So in that case, then, if we have a state that makes the mixing convergence happen super fast, it's a very strong type of convergence, might not be ideal because it might kind of like pull you away from the other memory states that you also might want to converge to, if that makes sense. Yeah, exactly. You're like overly fixated on this memory and not paying attention to the other memories that you also have potentially stored. But we'll cover that as well. So again, these are different parameters that you can play around with to get more of an intuition of like how this Hopfield network actually interacts. And there's also questions at the end, which will ask you stuff about this. So, might be good to play around with it. Okay, so that's the first thing that I want to talk about with the Hopfield networks, or the second thing, I guess, after the description. Now let's talk about the pattern search. So now we're saying like, there's this attractor state and there's this kind of like, it falls into this, the system falls into this attractor state, but like, how do we actually do that? How do we actually make the system, how do we design our system such that it has this specific memory state? So it's pretty simple. It's just the weights, the connectivity matrix would be just a dot product of the outer product of the stored pattern, divided by like the number of neurons that we have. But essentially what this is saying, the insight of this is that the connectivity matrix depends only on the representation that you want to store. If you have the representation that you want to store, then you can use the information just in that, to design a connectivity matrix that will make it so that your system will converge to this specific state, regardless of where you initialize it. So you would define in other words, you will first define the attractor state, and from the attractor state, you will construct the landscape, the configuration, the connectivity matrix. And that's kind of like, this is all this is saying, what I'm doing here is I'm only changing the configuration of the attractor state. And when I do that, we see that the calculated connectivity matrix is changing. But I'm not explicitly changing this. What I'm doing is only changing this. Okay, questions so far? Okay. Lastly, multiple pattern storages. Yeah. So this is kind of a trade-off. So like I said, if you want to kind of like bring it back to the brain, we're saying we have a certain number of neurons, which is, it's a fixed number, it's a limited number, right? But what we want to potentially be doing is to maximize the use of these limited capacity to encode as many memories as possible. So that sounds good, but it comes with a trade-off. We can store multiple different patterns, but the cost that we're paying for that is that the retrieval accuracy for each of them is going to be diminished. And you kind of like can think of it as, well, yeah, let me just keep going. So the way that, yeah, go ahead. So this is hmm, so that's a state. That's the connectivity matrix itself is not binary. So it's a real value. It can have many different like it spans a range. The lowest and the highest value can span a range. Now you can think of as when you're dividing it over 1 over n, it's like decimating all the weights by a specific amount, which I guess yeah, it would be the same result. It would be just be the effect of I don't think it's I'm not sure if this is true, but I don't think it would make a categorical distinction. I think it would just give you the same behavior, because essentially it's just multiplying everything by a scalar. Yeah. It makes, you can imagine it as making the landscape, like stretching down the landscape or stretching up the landscape. It will kind of like influence the rate of convergence, I think, maybe, but it will be applying it by a scalar would be more relevant when you have multiple pattern storages. Maybe like you want to kind of like scale, and this is, you can relate it to what I'm saying. When you have multiple patterns, what you can do, the way that you generate a configuration, a landscape that actually has all that patterns stored in it, is actually pretty straightforward. You just assume that you're designing a landscape for each of the patterns separately, and you just average them all together. And like the intuitive representation you can think of in your mind is like having a landscape where there's a stable point over here, and that's for pattern 1. The stable for it's another stable point over here for pattern 2, another one over here. So for a landscape that has all 3 of them, you just average these 3 landscapes together, and then you get all of them. Now the scalar effect comes more into becomes more prominent when you want to make one thing more steep than the other ones. So, and then you can assign different parameters to different yeah, it wouldn't really, I don't think it matters. I don't think so. Yeah, I think so. Yeah.
It's like that, it's like the average per neuron.
Yeah, it's just normalizing the number of neurons. But like, for example, let me just quickly go ahead real quick. In the last example that we have, we're actually assigning a different scalar parameter for different stored patterns as well, which will give us that kind of like, strength of convergence for different retractor states separately. Cool. Let's see. So in the example here, what I want to show. Yeah, okay. So this is, I'm just showing you that trade-off here in kind of like more numerical simulations. You can play around with how many patterns you want to mash into this connectivity matrix and see what is the retrievals. This is what is the success rate of the retrieval. So what I'm trying to do is recover pattern 1. I'm perturbing I'm making my initial state a perturbation of pattern 1. So let's see. Let's make it a, like, 1 pattern. If I get a single pattern, then the probability of success is 100%. If there's only 1 minimum in the landscape, and it'll converge into that minimum. But as I increase the number of stable patterns that I have, then the probability of success is diminishing. So, and this is kind of like, there's a random element to it, but 50% is the worst. So 50% means like 0 correlation, or like, well, yeah, 50% correlation, which means that they're orthogonal, they're independent. But as I increase it, 70%, we go lower, 20%, which is actually not that bad. So another point here is that there's a symmetry this is like this is another question in the assignments, which is in hot field networks, there's a symmetry between a attractor state and its opposite. So if this is like, so here it might seem like that the retrieve state is pretty low considering that the overlap is 20%. But what we really care about is the if it matches with this the state that we're seeing here or with this mirror image. There's because of that. Well, I'll leave you to kind of like ponder why that is, but keep that in mind as well. In any case, what I want to show you in this example is that sense of interference of different memories together, and how we can mitigate that by changing the number of updating iterations that we have, or by changing the number of patterns that we have, or the number of neurons that we have. So like just intuitively, what do you think would be the effect of increasing the total number of our neurons in our network in its ability to encode multiple different memories? If we increase the total number of neurons in our network, how would that affect the capacity of the network to encode more memories? Would it make it a better model to encode more memories or make it worse? So imagine like I have 10 neurons and I'm trying to embed 3 memories in it, 3 attractor states into it, right? And it's like, giving me a success rate of like 80%. What happens if I change that, change the system from 10 neurons to 100 neurons? How do you think it will affect its capacity to retrieve its memory states without interference?
It will increase it.
That's a good question because I see like a lot of fun. Huh? There's an effect of iteration, but if we just focus on the effect of the capacity of the network itself, let's fix the iterations, let's say in 50 or in 100 iterations.
That is interesting. That's like, what's the ratio between how many neurons you have and how many patterns? And then it's like, is more complexity necessarily better? And is there like an optimal number to try and find that? That's because like you have too little neurons.
Yeah.
You're just like, there's no way that you can find all these different patterns. But you have like too many neurons, it might get overcomplicated, might take too much iteration.
It would certainly increase the computational cost because you have more neurons to kind of simulate.
I think if you have more neurons, you're more likely to be able to find more patterns.
Yeah, exactly. And you can think of it as this: you just expand the size of your landscape in a metaphorical way to be just larger. So if you have a larger landscape, even though you have wells like spread across it, they're separate enough that they wouldn't necessarily interfere with each other. But if you have a very small landscape, the probability of them interfering and the one valley like overlapping with another one and kind of like mixing things up would increase. So this is what's happening here. So let's just go back to like 45 iterations. Yeah, okay. If right now it's like 40%, pretty bad. What if I increase it to 18? Oh, 88%. That's much better. So yeah, you can play around with these parameters as well to, build your intuition more. Okay, so that was a quick run through of hot field models. Hopefully, like, you get a better intuition of like what it's supposed to represent and, what it means. And now for the last part is to bring back that biological complexity that we added in first. So the hot field model was very binary. It was very bare bone, and it wasn't necessarily supposed to have a lot of biological biological complexity in it. But now we're gonna bring back what we learned from parts 1 to 3, the exponential capturing the synaptic transmission, the rates to the convolution of the spike trains, and now we're gonna use that to build a more physiological hot field. So the way that we're doing that, it's again not that complicated, but essentially what we're doing is we're swapping out that kind of like communication between the neurons. So it's no longer just multiplying the matrix by the state itself, the positive state multiplied by the matrix. It actually goes through that process of, is this spiking right now? If so, I'm going to convolve it with that kernel that I showed you before. And if so, would the postsynaptic potential fall over a certain threshold? And if so, it's going to generate a spiking neuron. And if so, then I will see if it's spiking or not, and I then bring in the hot field intuitions. So this is just a code demonstrating that, putting it all together. I mean, it's not as biological as it could be, but it's just to show you we can actually do that. We can bring the different modules that we went through and we can put them together to generate something that has like all of them incorporated. So this is the impulse response function that we can define here. This is a spike train for a particular neuron. And this is the postsynaptic potential, and we're thresholding it. And we're saying that, for example, if you want to store this pattern, we want to store this pattern in our hot field matrix, but we want to also include this sort of communications between neurons, would be able to retrieve our pattern back. And in this case, for example, you're seeing that, yeah, it's actually doing a pretty good job. Again, there's a symmetry between this state and this mirror image. So even though this is flipped, it's actually that still counts. So even though we're kind of like making the hot field model a bit more complex, we can put these together and kind of like, generate a more physiological model that would also have that sort of memory mechanism, the emergent memory mechanism embedded in it. So hopefully you kind of got a bit more excited about what you can do with the hot field networks and the applications of it. And any further questions? I think there's one in the chat.
A question from Sharon, which I think, we had a version of that discussion just now. Does retrieval accuracy diminish because the stored patterns interfere as their number grows, or for another reason?
Yeah, I think it's primarily that, the interference of different attractor states. So you can kind of think of the attractor states as local minima, right? And when you get a local minima, then you have an attractor state, you have a memory state. But now imagine in your mind that in this landscape that you have, there are two very similar, very close attractor states, two very close wells or valleys or attractor states. It might be the case that if they get too close, the attractor of one actually gets let me see if I can just draw here. 1 second. So imagine you have a landscape where you have, this is a horrible color. Hold on. How can I change the color? Is there a way? Welp. I'll just draw on top of this. Give me 1 second. There we go. Whew. So imagine where we have one attractor state here, another attractor state here. I mean, this is fine because they're far apart and each of them actually have their own local minimum, right? But if we have if we cram these together, what we might end up is a configuration that would look like this. One over here, something like this. So this is supposed to be one attractor state over here and another attractor state over here, but you can see that they interfere with each other and you no longer get necessarily a minimum over here. You just get like a diminishing of the slope, but it never really becomes a local minimum. So then you kind of like lose this memory. They interfere with each other. Or, for example, even though the attractor state of this hill right here should have been like somewhere over here, because now it's being influenced by this attractor state over here, the minimum is being shifted a bit to the side. So what you would retrieve is something similar to the memory, but it's kind of like messed up. Kind of like, it's like saying, you can think of it as like, going to the mall and seeing your friend. I mean, you kind of like mix up memories all the time as well, like, just going to the mall or seeing your friend and they're wearing the same, they're wearing the same clothes. One time they're, this is getting out of hand, but it's just you mix up the context and what happened because they're just too similar. So you kind of like mix up memories. Hopefully that makes somewhat of an intuitive sense. And hopefully this graph is making a intuitive sense. Color is great. Is there a limit for this this in Hopfield model? Is there a limit? I think it just gradually decreases until you gradually converge to a state where it just becomes random noise. I don't know if there's a specific optimum. I don't think there is. I think it just scales negatively with the number of patterns you include. Well, interestingly, this is one of the assignments that you guys are supposed to play with and fill out, which is actually exploring the effects of increasing number of memories into its retrieval accuracy. So yeah, maybe you can tell me afterwards. Any other questions? Cool. Cool. Okay. Hopefully you enjoyed it. And thank you very much. Thank you. Thank you.
Okay, so we're going to wrap up, guys. Thanks for those who were on the call joining in. Great questions from the room. As Parza mentioned, just finishing up there, thanks. What's coming up is the assignments. So assignment 1 will be released next week or the week after. And as we mentioned previously as well, like the structure of these will be very similar to the I mean, literally like extensions of the collab notebooks. So that's kind of how they're going to appear. They're going to be kind of exercises that are like extending what you've seen in those tutorials. And yeah, so thanks everyone for attending. Please keep your feedback coming on the forum. So like if something occurs to you to ask a question about that's interesting, go and like drop a message on the Moodle system. Like I really want to kind of generate some questions and some discussion on there. Like we've had some great questions and discussion on the chat. And I guess worth noting for those who care that there is a participation mark. So dropping a few interesting questions here and there might be something that secures you that 10%, if that 10% is something that you really care about. No comment on whether you really should or not. Okay, thanks a lot, guys. See you next week.